Hello everyone, this is Gokul Alex. Welcome back to my YouTube channel. Today we are going through one of the most beautiful concepts in the history of algorithms. It is known as Kalman filters. Kalman filters originated in 1960s and it has been applied for historic missions, projects, systems and platforms ever since. Let us try to understand the origins and the concepts behind Kalman filters. Kalman filters emerged as an alternative to a very powerful concept known as an Wiener filter, another signal processing concept, which was invented by a very famous computer scientist known as Norbert Wiener. Wiener filter required infinite amount of past data based on stationary processes. When we talk about infinite amount of past data, now we know even today we have very powerful machines which learn from infinite amount of past data. The same problem was a challenge for a lot of mission critical projects even in 1960s. That is the reason why in the world of mission critical projects, they were looking for an alternative to Wiener filter. Norbert Wiener employed a frequency domain approach, which could only work in offline mode as we need to process entire data set at once. However, real systems like rockets are non-stationary processes. Not only rockets, aircrafts, vehicles, and beyond, they are all working on real time. You need computer algorithms which can process data in real time. This is one of the challenge in front of the Wiener filter. Thus, there was a desperate need for a time domain solution, and it need to be recursive because the recursive approaches helps us to solve a lot of problems in a very seamless manner, in a very in a and we could employ a lot of powerful algorithms when it is a recursive time domain solution. And we have to understand this invention happened in 1960s, where we don't have the luxury of the GPUs and the TPUs of today. So, a famous Hungarian mathematician and a computer scientist known as Rudolf Kalman, who was in United States at this time, he worked on the control theory with a pioneer, John Ragazzini, in Columbia University. Rudolf Kalman also worked in Bell Labs. He worked with luminaries like John Tukey, Solomon Lefschetz, and Henrietta Midonik. So this is the person who invented Kalman filters. So to summarize the influences on Rudolf Kalman, we have to understand Wiener filter problem was on the table, and he also derived influence from Lyapunov's stability theory, which is another formidable theory in control systems. And the second influence was from the study of state space representations in Bell Labs, especially for time domain. As we know, even today, when we think about state space representations, you must be thinking about even to the models like Mamba and beyond. latent state space representations are becoming very important even for large language models. So there has been an very early research on state space representation in Bell Labs for time domain. And the third major influence on Rudolf Kalman was the orthogonal projection in Hilbert space based on work from another visionary called Andrei Kolmogorov. So these are the three major influences which helped Rudolf Kalman to come up with Kalman filters. Rudolf Kalman was visiting Stanley Schmidt at NASA Ames Research Center. They discussed the problem, how to estimate the rocket position from noisy radar data. The existing approach was to process all the past data, which was infeasible at that time. We know that when you look at a rocket, it cannot process all the past data in the real time because it is processing so much of data, and we are talking about a rocket, and those days you can't afford the GBs and TBs of storage. You're dealing with kilobytes of computational capacity. So at this time, previously in Bell Labs, Kalman, Bertram, and Sarachik, they had already worked on state space representation models. And as we mentioned before, Kalman also derived inspiration from the orthogonal projection lemma envisioned by Andrei Kolmogorov and later expanded by Norbert Wiener. This is one of the lemma which helped Norbert Wiener to customize his frequency domain approach and extend the Wiener filter to Wiener-Kolmogorov filter. So how did Rudolf Kalman synthesized Kalman filter? He brought together these powerful concepts: state space model for dynamics in time domain, and recursive least squares for updates, orthogonal projections for optimality. Thus, the core concept in Kalman filter is it is a recursive system with no need to store past data, just using the current estimate. And it works in a dual mode by filtering forward and smoothing backward. This is a very powerful ingenuity in the Kalman filter. And it is again a very efficient system employing algebraic approach with elegant matrix equations. Thus, Rudolf Kalman's filter consists of a set of equations. First equation is equation to predict the state and the covariance. The concept of state is a very deep concept which we have to study in detail, and we will have a lot of sessions in the future to understand more about state space systems. The second in the set of equation is to derive a factor or a coefficient known as Kalman gain. And the third factor is the equation for the state update. So first you predict the state and covariance, then you derive the Kalman gain, then using this Kalman gain and the earlier predictions, you come up with the equation for the state update. Let us understand the variables used in the equations before seeing the equations. First variable is the state estimate related variable, a variable for error covariance, state transition metrics, and then a control metrics, a measurement metrics defined by H, Z, a measurement variable, R, a measurement noise variable, Q, a variable to denote the process noise inherent in the process, and K for Kalman gain. So the first equation, the state projection equation, it's actually a equation where you predict the time updates. It's a prediction step for time update. In this equation, we have seen it uses both A and B. The state model project forward in time before looking at the actual values. This equation means that the new state is an old state moved by the physics model plus any change due to the control inputs. So before taking any sensor data, it comes up with a physics model for the new state based on the old state. And then the second equation is to project the error. The error or the noise, you're projecting it, the uncertainty P grows when the prediction moves forward. So we are adding uncertainty inherent in the system. The system uncertainty is represented by the process noise Q. So we have two important variables here. We have seen A in the, as we have seen in the previously in the variable system, A is the state transition and B is the control matrix. So in the error projection, we have A and A transpose, and we have the covariance related, the P represents the error covariance. So we are calculating the error covariance using the state transition plus the process noise. So system uncertainty is growing with respect to the process noise. The third important equation is the Kalman gain factor. The Kalman gain factor is calculated with the combination of the P, H, the measurement noise, and then what we do is we take the multiple of H with the error covariance P and the transpose of H, plus there is an R, which is another, the measurement noise variable. If you see here, we can see R is the measurement noise variable. So, and then this is coming in the, in the denominator. So this calculate the optimal weighing factor. If the measurement noise R is small, K will be large. As we see, if the R is going to be small, the K value, the Kalman gain will be large. That means if the prediction uncertainty, when you are measuring it from a sensor, if the noise is small, then we have to give a large value for the Kalman gain. If the prediction uncertainty is small, the K factor will be small. So that means you don't need to add, the gain factor will be less when the uncertainty, they are directly proportional, right? So then the final equation, this is the final estimate, this is the predicted estimate plus a correction. The term ZK minus HXK is called the innovation factor. It is the difference between what the sensor says and what we expect. So this in this and there is one more equation. Finally, the error the state update. In this equation, we are incorporating all the factors we have identified in the previous equations: the Kalman gain, the measurement, the covariance factor. All of them comes together. The uncertainty decreases when based on the gain from the measurement. So this is a very intuitive equation. As per this equation, the set of equations, if the sensor is very noisy with high R, with high measurement noise, the filter sets the Kalman gain to 0. The equation becomes xk almost equivalent to x minus 1 to k. The filter ignores the sensor and relies on the physical model. If the sensor is very precise with low measurement noise, filter sets Kalman gain almost equivalent to 1. The equation pulls xk towards the measurement factor. So this Kalman filter immediately was a runaway hit. It was tested on the spacecraft, navigation problems. That's like a dream come true for any algorithm, right? Immediately it was tested. The first implementation in 1961 on Apollo trajectory estimation. It could run on Apollo guidance computer that had just 64 KB memory. Beyond, then because of this attention and the success of the Kalman filter, lot of mathematical rigor has come into it. Initially, Kalman presented this filter as a deterministic linear algebraic system, but it was in 1961, 1 year after, Stratonovich in Russia showed it was Bayesian, and later in 64, Ho and Lee explicitly derived it from Bayes' theorem. Thus, it is considered as a Bayesian inference for linear Gaussian systems. That is something we have to go deep dive in subsequent video sessions on Kalman filter and beyond. So Kalman filter's story is not ending here. Kalman filter has been extended beyond in a more rigorous system into extended Kalman filter and nonlinear for nonlinear systems and filters such as particle filter and etc. So Kalman filter literally opened a new pathway for the probabilistic systems and probabilistic algorithms. And this is like the combination of so many beautiful concepts which existed in the early 1950s. Thank you so much for watching this video. If you like this video, please subscribe to this YouTube channel and share this video in your circles. Thank you so much.